This podcast is brought to you by the School of Advanced Study, University of London.
So we welcome today Professor Charles Withers, Professor of Historical Geography at the University of Edinburgh. Professor Withers published an impressive amount of works with a focus on Enlightenment and geography, among others, such as Placing the Enlightenment, which was released in 2005, if I'm not mistaken, as well as Incursions in the 19th century. I think of your work on the British Association for the Advancement of Science, published in 2010. So today's talk will explore the historical geographies of the Prime Meridian, the case of France and Britain in the 18th century.
Daniel, thank you very much indeed for that introduction. Thank you very much indeed for the invitation to come to Paris. It's a great pleasure to be here, and thank you for your generous hospitality. I should say that this paper is part of a bigger project on the geographies of the Prime Meridian, the Premier Méridien. I'm most grateful to you for the opportunity to rehearse something of my arguments on this. My interpretation of the 18th century in what follows is an extremely generous interpretation. For reasons you'll see, it stretches from 1634 to 1830, but actually in terms of detail it's more from the 1770s through to the end of the 1820s. Let me provide some background and then into the detail and the meat of my talk. The Prime Meridian is the line at which the world's longitude is set at 0 degrees. Both longitude on the one hand and time's measurement on the other are based on the Prime Meridian. Now, since 1884, the Prime Meridian has been fixed at the Royal Observatory at Greenwich in the United Kingdom. And global space was, if you like, universally and cartographically regulated from that moment in time. And universal coordinated time, or to give it an earlier description, Greenwich Mean Time, GMT, was set from that point in space. Now, the fact that Greenwich is the ground zero of planetary measurement is the result of the International Prime Meridian Conference. This was a meeting that lasted for a month in Washington, D.C. in October and the early days of November in 1884. Now, as he welcomed delegates to Washington, D.C. on the morning of the 1st of October, 1884, the chair of the conference, Rear Admiral C.R.P. Rogers of the United States Navy, spoke of how delegates renowned in diplomacy and science, the phrase is an interesting one and I'll come back to it, had come to the American capital at the invitation of the President of the United States, and I quote, seeking to create a new accord among the nations by agreeing upon a meridian proper to be employed as a common zero of longitude and standard of time throughout the world. A month later, 1st of November 1884, Rogers closed the meeting. And he closed the meeting following delegates' near unanimous agreement upon 7 resolutions over a global prime meridian and universal time. Now, key amongst these resolutions, not all 7 are on the picture here, but key amongst these 7 resolutions was the acceptance of the conference that there would be a single prime meridian for the whole world. That's resolution 1, for all nations. Recognition that Greenwich in the United Kingdom should be the world's initial meridian for longitude. That was resolution 2. Resolution 4 was that there would be a universal day, a 24-hour agreed day. And resolution 5, that this universal day should begin for all the world at the moment of mean midnight at the initial meridian. In other words, a 24-hour clock and your days changed at midnight based on Greenwich time. Now, for contemporaries, the fixing in 1884 of the world's prime meridian at Greenwich, and with it the global establishment of universal time, was a momentous event, or at least it had the potential to be so. But for modern scholars now, the Washington meeting, 1884 and all that, if you like, have together been seen as vital moments in global science, cosmopolitan politics, and indeed for one literary scholar recently, the very shaping of modernity, as Andrew Barrow has it. Now, this is background because it's not the story of my paper. In these terms, we have Washington, Greenwich, 1884 and all that as the solution. But the solution, quite to what? If this is the solution, what's the problem? Well, the clues lie in Admiral Rogers' words, seeking to create an accord among the nations by agreeing upon a meridian proper to be employed as a common zero of longitude and standard of time throughout the world. The problem of the prime meridian before 1884 is that there are at least 30 different prime meridians at work in the world. The problem is that there is no standard time. The problem is that there is no agreed civil day. Different notions of timekeeping worked in different places. At one time or another then, over 30 different places across the world were employed as initial prime or first meridian. The terms are interchangeable. Washington, Philadelphia, Toledo, New Orleans, St. Paul's Cathedral, but not Greenwich, St. Paul's Cathedral in London. The Canary Islands, Paris, St. Petersburg, or even, as one 18th century commentator has it in relation to Enlightenment ideas about universal history, the manger in Bethlehem. Here then is John Senex, map maker and geographer to Queen Anne, writing in his 1721 New General Atlas, and it's a lengthy quote, and let me emphasize one or 2 points in it. The Western nations, though the Western nations agree to fix it, he's talking about the prime meridian, to the west of our continent, they do not agree on the place where. Ptolemy and the ancients fixed it at one of the Fortunate Isles, now generally supposed to be the Canaries. Some of the Arabians followed him. Some moderns would fix it at Terceira, others at the Isles of Cape Verde, or Cape Verde itself, some at the Pike of Tenerife, one of the Canaries. The Spaniards would have it at Toledo, the Portuguese at Lisbon, and in short, every nation may fix it at their own capital if they please. The difference among them, and John Senex is here talking about the different geographers, not the different prime meridians, the difference among them about fixing this meridian has made great confusion in their maps, occasioned much difficulty in finding the longitude of places. The only way to remedy this is to give an account of the different places where they fixed their meridians and of their distance one from another. So if 1884 is the solution, the problem is that in using different longitudes, nobody knew where you were starting from in terms of time or space. Paris, Greenwich, Toledo, all would have their zeros. There would be a different astronomical zero and a different topographical zero. You and I could all leave this room now and go and describe a zero line from the Boulevard Saint-Michel or Boulevard Saint-Germain, and that would be our start point for mapping the world. But if we don't share that zero with other geographers, how do we know where we start from? That's the problem of the prime meridian, astronomically and geographically. And there are over 30 of these prime meridians before 1884. This paper then is about two of them. It's about Paris and it's about Greenwich, and it's about the relationships between them in the period between 1634 to about 1830, although the bulk of my story is in the period 1770 to about 1820. It's actually a story that's much less about geography. You may be pleased to hear this. It's actually about the politics and authority of science. It's about accuracy and precision, and it's about the tolerance of error, the tolerance of inaccuracy as nations delimited themselves. So let me begin my story then in mid-Atlantic in 1634. In July of 1634, as the result of a conference overseen by Cardinal Richelieu, King Louis XIII of France identified Cap Farrow in the Canaries as the prime meridian for France. This seemingly endorsed the Ptolemaic choice of the prime meridian, but in fact the French ruling in 1634 was rooted in the politics of war with Spain, not in Ptolemaic claims. The French affirmation then of Cap Farrow was part of contemporary diplomacy over maritime conflict in relation to the 30 Years' War, 1618 to 1648. The King's decree essentially stated that Spanish and Portuguese ships were not to attack French shipping in waters to the east of this first meridian and north of the Tropic of Cancer. Now, you can place this demarcation line, if you like, in relation to contemporary intellectual debates over the legal jurisdiction of the oceans. But Louis XIII's decision in 1634 is a matter not of geographical consensus. It is in fact a statement about the pragmatism of absolutism, the pragmatism of an absolutist king. Now, against this evidence of, let me call it, French realpolitik in the 1630s, we must also weigh the practices of oceanic navigators themselves. The evidence for that comes from ships' logbooks. Contrary to the view, then, of one commentator that Louis XIII's declaration had the effect of encouraging the use of ferro, Cap Faro, El Hierro, there were marked differences, in fact, within the French maritime community regarding the use and recognition of ferro as that meridian. If we look at logbooks, it is not ferro which predominates in French oceanic navigation. It's either Tenerife or it's the Cape Verde Islands. French ships bound for the East Indies would take Cape Verde as their zero. Those on triangular voyages across the Atlantic, France, West Africa, the Americas back to France, would use the Canaries as their base meridian. So the importance of ships' logs points to differences in customary usage regarding the prime meridian, within as well as between different national user groups. But in map making, by contrast, the situation is rather different. The Faro prime meridian appears as an initial meridian in French cartography decades after Paris has been adopted as the nation's longitudinal baseline from the 1720s. And I'll come to Paris's adoption as the formal French prime meridian from the 1720s in just a minute. But this is a French map of the mid-1750s, and the line that is marked on it, Premier Méridien par l'ordre Louis XIII, 1634. And the prime meridian line, 0, goes through Faro, 1751, 30 years after Paris has been established as the formal 0 running through the observatory, to which I'll come in a moment. So the story is a complicated one. National differences is one way of reading it. Communities of difference within nations is another. What then does all this mean? Well, what it means, and indeed, why does it matter? Well, what it means is that the prime meridian was a matter of scholarly disputation and of differences in regard to tacit expertise, kingly decree, and, if you like, practical usage. The prime meridian, but differently positioned, is associated with the seafaring and earth-ruling colonial activities of what, following people like John Brewer, we can think of as the 18th century fiscal military state. Its different positioning was differently approached through the agency of authoritative print, geography books, atlases and so on, in verifiable experimentation, to which I'll come in a moment, and of course in replicable calculation. People were astronomically measuring and trying to position where this line would be. The depiction of different prime meridians on maps and charts was bound up with what Matthew Edney has called modes of Enlightenment cartographic culture, modes concerned particularly with questions of accuracy. Again, against that background, let me focus in a little more detail yet and look at two themes in particular. Firstly, the emergence of Paris as the site of France's observed, that is astronomical 0, and its geographical 0. And the second element of my story is about the transnational fixing of Paris and of Greenwich from the 1770s and 1780s. Try as people might, neither Paris nor Greenwich would stay still to be measured. The establishment in 1666 of the Académie Royale des Sciences de Paris under the direction of Louis XIV and Jean-Baptiste Colbert, and the building of the Paris Observatory a year later, together constitute, as we know, a new and important beginning for natural philosophy in France, and for the prime meridian in particular. Astronomical and topographical studies were advanced. They were so under the direction of the Italian mapmaker and the mathematician Giovanni Domenico Cassini, usually known now as Jean-Dominique Cassini, or Cassini first, Cassini I. The related astronomical and terrestrial measurement studies of Jean-Félix Picard, author of Mesures de la Terre in 1671, underlay 8 years later the production of the Connaissance des Temps, the Paris-based ephemeris, containing tables giving the calculated position of the sun, moon, and other heavenly bodies, and using Paris as the zero for those calculations. So from the early 1680s then, France's topographical measurement is begun to new standards, new coordinated plans of trigonometry and triangulation. But this new beginning for science, for France, and indeed for the Prime Meridian, remember only 40 years before, Louis XIII has ordained Cap Pharo as the Prime Meridian. This new beginning for the idea of France as a territory and a polity that is produced through geography encounters two related problems, and encounters them right at the beginning of this work. The first of them is that France is shrunk. As the mapmakers and astronomers measure France, they actually shrink it by several hundred square miles, notably on the nation's western and Mediterranean coast. People will know this map of 1693, I'm sure. The second is the persistent difficulty of accurately fixing the prime meridian baseline against which France might be measured at all, and of calculating thus in longitudinal terms where Paris was. And indeed, if you don't know where Paris was longitudinally, geographically and astronomically, what is the shape and extent of the country? Where did Paris stand in relation to Cap Pharo? Colbert, Picard and others then reduced their nation. They were the first to use Paris as the nation's first meridian in 1693. But where exactly was Cap Pharo, where the king had ordained France's prime meridian to be in 1634? The search for accuracy in answering these questions actually points to a series of work which is about France's refashioning, France's topographical emergence, if you like, into new national limits from the end of the 17th century. The problem was that the 1634 edict, based as it was upon one imprecisely located classical prime meridian, Cap Pharo, and upon royal whim, 1634, Louis XIII, a conference organised by Richelieu, was determined by politics, not by precision. Cap Pharo offered no basis for accurate astronomical observations, no basis for the mathematical calculation of terrestrial limits, thus to judge the extent westwards of France. Because this essentially Ptolemaic prime meridian was not fixed, longitudinally speaking, it could not be France's zero in anything other than a symbolic way. It had to be Paris. There's an essential distinction then between the emergence of Paris in the 1720s as the observed astronomical meridian and a geographical meridian that effectively from 1634 is political fancy, it's political whim. Now, addressing these issues between the last decade of the 17th century and, well, let's say the mid-1740s, France's astronomers, mathematicians and geographers lead the world in producing what might be regarded as the first modern corpus of material specifically focused upon the prime meridian as the basis to national identity through geographical work. This is evident in a remarkable cumulative genealogy of observational recording, correspondence, debates, maps and texts. Inquiries of 1702 by the philosopher-mathematician Jean-Joseph Lamontre. He distinguishes between the geographical and the astronomical meridian. Philippe de la Hire's 1704 Description et Explication des Globes. It includes this body of work, a very lengthy memoir of 1722 from Guillaume de Lille, Géographe de l'Académie, and from 1718, Géographe de Roi, to the infant King Louis XV. And de Lille is important because he proposes, for reasons of convenience, a figure simply, he says, of 20 degrees difference between Cap Pharo and the Paris Observatory. But a central document that is of different sort in this corpus is the work of Louis Feuilly in 1724. Important because he's the first person to voyage to the Canaries to try to determine at first hand the longitude of Cap Pharo. He, if you like, is the Enlightenment's first geodetic expedition. He aims to determine the prime meridian as it runs through Cap Pharo in order to legitimise the positioning of Paris as the astronomical observatory and the astronomical prime meridian from the 1720s. In contrast to Delisle, however, he computes the difference. He doesn't say, let's work for convenience and it'll be 20 degrees. He computes the difference and makes it a difference in longitude of a little over 19 degrees. Leave that figure and this point about declaration and computation in the back of your minds, and I'll return to it. The culmination of this enormously important, world-leading French work, however, is Cassini de Thury's La Méridienne de l'Observatoire Royal de Paris, usually known, published in 1744, as Méridienne vérifiée, an encyclopedic inquiry which runs to 292 pages, with a further 250 pages of supporting titles of astronomical and longitudinal calculations. And what he produces as part of this is, again, I'm sure you're familiar with this map, the Carte de France of 1744 by Cassini the second. So, cutting a lot of this of the detail out, what emerges between 1693 and 1744 is that Paris moves to and becomes the centre of France's increasingly self-confident national calculation. Its prime meridian is not just le méridien, one prime meridian amongst the geographical and astronomical many, but it is la méridienne, the prime meridian, the nation's ruling line, and quite possibly, of course, the world's ruling line. Let me come back, though, to this issue about Delisle's let's make it 20 degrees for convenience and the computations of Feuilly over a little over 19 degrees. Statements of accuracy are also statements about a tolerance of error. For the French, and because of the ease of calculation, it's Delisle's figure of 20 degrees for the longitudinal difference between Paris and Cap Pharo, and not Fouillet's more accurate figure of 19 degrees 55 minutes and 3 seconds west, as he calculates it, that is used throughout the 18th century. In fact, it's actually used into the 19th century. And it's used despite further expeditions and the work of the Dépôt des Caps et Plans de la Marine after 1720, which of course calculate that it's not 20 degrees. Even the revised calculations of the distinguished astronomer Pierre Le Monnier in 1742, that the actual figure, in inverted commas, the actual figure was 20 degrees 2 minutes 30 seconds, are overlooked. They're overlooked simply in favour of the expediency of convenience and established practice using an approximate figure of 20 degrees. So the authority of the Paris prime meridian, and possibly la méridienne, lay in the claims of those astronomers, geographers and natural philosophers who professed it, and in their advocacy of accuracy. This advocacy of accuracy is at once, if you will, a philosophical and scientific necessity, and a cumulative process involving field work, sedentary reflection and complex computation, even if you like, and Ken Alder has discussed something of this in his work on the meter, even approximating to something like a moral quest that would be expressed and reduced to numbers. The argument fixed the prime meridian, and France's geographical limits would be firmly known. Its capital astronomically determined, the Académie des Sciences' position as a state-sponsored institution would be strengthened, its members' standing would be enhanced. So for France, between about 1720 and 1744, what Jean-Pierre Martin has called 1744 a monumental year in the history of Enlightenment geodesy, this interpretation is lent support by the parallel endeavours of French academicians who are then engaged, of course, in terrestrial measurement in South America as part of expeditions then testing competing theories about the shape of the Earth. The meridian-related work of people like Charles de la Condamine, Pierre Bouguer in the Amazon, and Maupertuis as he's heading towards Lapland is part of this story. Mathematics was the language being used to realise and reduce the world to empirical order. Trigonometry, cartography and triangulation here, 1744 map with the meridian of Paris running north-south, and you can just make out a series of triangles, about 820 different triangulation schemes to reduce France to geometric order. But this interpretation of the Paris meridian as something realised through mathematical inquiry within the confines of a state-led learned society and its associated activities in the 50 years after 1693, and particularly in the quarter century from 1720 to 1744, must be balanced by my earlier remarks about French maritime practices, by the likelihood that, of course, Cap Farrow was never widely practically used by the French before or after 1634, even though, to go back an item, it appears on maps in 1750s here as the line showing the 1634 line here. Okay, let me turn to the British evidence. It's a Franco-British seminar, so the other side of the hyphen for a moment, and then to come to complicate the story a little more. For British mariners before the mid-18th century, the common practice regarding the use of a prime meridian was actually much more variable but also more pragmatic than either the Dutch or the French. British oceanic practice would be simply to take, as Yonkers, the historian of geomagnetism, puts it, the more utilitarian principle of taking the last land sighted. But there were differences between the ships of the East India Company and the ships of the Royal Navy. The ships of the Royal Navy adopted the use of a prime meridian based on London, and I mean London, not Greenwich, earlier and more consistently than their East India counterparts. All changes in the British experience in the 1760s. In 1763, the British Astronomer Royal, Neville Maskelyne, publishes the British Mariner's Guide. And he there calculates all the longitudes from the meridian of the Royal Observatory at Greenwich, which is only 5 minutes 37 seconds of longitude to the east of St Paul's Cathedral in London. Remember that that was one of the earlier prime meridians in use. From 1765, Neville Maskelyne drew together proposals for a nautical ephemeris based upon his lunar distance observations for longitude, and in late 1766, Maskelyne oversees the publication of the Nautical Almanac and Astronomical Ephemeris for the year 1767. So it's looking ahead. In other words, it's a predictive text. Based on astronomical positions, you'll be able to identify and keep time at sea in relation to the advance of John Harrison's chronometer. Crucially, Maskelyne based his ephemeris, and John Harrison sets his new marine chronometer to the 0 meridian at Greenwich, not anything else, not the St Paul's Church in London. Now, I'm not laying, I hope, too much emphasis upon Maskelyne's nautical almanac. We know that it depends in part upon the German natural philosopher Tobias Mayer's tabulations for its structure, and it's certainly not the first ephemeris. In France, Abbé Nicolas Louis de Lacaille had demonstrated the value of lunar distance observations and incorporated them in the Connaissance des Temps from 1761, and used the prime meridian of Paris for his tables. But from 1774 to 1788, the Connaissance des Temps incorporates Maskelyne's lunar distance tables based on Greenwich, alongside Paris-based prime meridian tables. And indeed, the 1789 version even uses the British tables converted to the Paris meridian. So what I'd like you to think about is the authority, yes, for the British experience of the Nautical Almanac from 1767, but it very quickly becomes a hybrid text in the incorporating of other nations' prime meridian evidence. The Greenwich tables, in fact, are also included in the Spanish Almanaque Nautico from 1792. What's the point? Get to the point, Charlie. Well, the point is this. The point is that across Europe, on maps, in geography books, and in maritime navigation, different prime meridians continued in use long after the establishment of the Paris Observatory, long after the establishment and the publication of Connaissance des Temps, long after the establishment of Greenwich's Royal Observatory and the Nautical Almanac, though they had the effect of securing, if you will, the prime meridians on the one hand of Paris and of Greenwich. So what you find, and the detail of this will not be clear, it's one of these giant maps that you kind of have to spread out and examine very carefully. You will find different prime meridians appearing on topographic and hydrographic charts to reflect the several referent points then in use by map makers and by sailors. This is one Neptune Occidental of 1778, showing 6 different prime meridians. From north to south, the Azores, the western side of Ferro, from the Pike of Tenerife, the peak of Tenerife, it's the volcanic cone. From the Lizard, the most westerly point from which ships would regard the last land sighted. From London, and note that's London, so not St Paul's Cathedral, not Greenwich, and Paris is one of the 6 on this line. Now this information is vitally important with respect to navigation in coastal waters. Where do you start? If you have more or less a notion of your speed, you need to know where your zero was. How far have I gone? Where am I actually in navigational terms? Of these meridians on this map, in fact, only Paris and Cadiz are prime meridians on the basis of observed astronomical reckoning. All the rest are simply geographical start points. So the further evidence from within Britain that the primacy of Greenwich is, if you like, being denied after 1767 comes from this quote here from Thomas Jeffreys, who is geographer to King George III and produces, or Jeffreys does so posthumely, but this is his editor speaking, a book called The West India Atlas of 1775. So listen to the words carefully, given all of what I've said up to now. For a first meridian, we have made use of that of the island of Ferro, the most westerly of the Canaries, marking beside at the top of each chart the difference of longitude from the meridian of London. This is 1775, 8 years after Maskelyne's authorization of Greenwich. Here in England, we unhappily have not been sufficiently agreed upon a first meridian, which some reckon from St Paul's at London, others from the Royal Observatory at Greenwich, several from the Lizard Point in Cornwall, the last land sighted. These differences in meridians produce a perplexity in the reductions we are obliged to make in comparing charts with one another. He ends this quote, "We could make a large catalogue of meridians which caprice and national pride have led different authors to make use of." In sum, it matters where you look for explanation of these facts and of their consequences. Books of geography and of astronomy taught that there were different prime meridians, but they also show that it is only slowly, in fact, in the 1780s that Greenwich is accepted in Britain. Paris is accepted earlier in France, but not by the maritime communities. In Spain, Cadiz, Toledo and Madrid all continue as national prime meridians throughout the 18th century. The prime meridian is also taught as a practical proposition, but at sea, what ruled was expediency, not a single prime meridian. What is also clear, and now let me, in the last 10 minutes or so, is that okay for time, turn to a conclusion to make the story a wee bit more complicated yet. Because by the 1780s and by the late 1770s and 1780s, I beg your pardon, astronomers and geographers in Paris and in Greenwich were acutely aware of these differences in the utility of different prime meridians. They were acutely aware that knowing the world depended where you started from, and relatedly, that the start point or start points to longitude's verification could be accurately determined. Let's go back to the French evidence. Cassini de Thury's 1744 Méridienne vérifiée, the Carte de France 1744. We know it establishes new dimensions for France's view of itself, but it also has the effect of contradicting and exposing inaccuracies in Jean-Félix Picard's astronomical measurements of the 1690s. Now, the difference, the inaccuracy is fairly small. It's about 5 toise, T-O-I-S-E, how do you pronounce that? Toise, yeah. Or about 10 meters or so. But had this been multiplied for France as a whole, then the placing of the Paris Prime Meridian would be, if you like, in the wrong position. The error would have been compounded for the nation as a whole. So, because Cassini de Thury's Nouvelle Carte de la France, this one here of 1744, presents a view of France which, in the king's eyes, is essentially abstract and geometric, Louis XV asks Cassini III to map the nation anew, to begin again. Now, upon Cassini de Thury's death in 1784, this project is continued by his son Jean-Dominique, Comte de Cassini IV. But by then, of course, we know that royal authority is waning, and during the revolution, the Cassini's project is never completed. It's effectively nationalised. And of course, it's bound up in this period, part of the story into which I won't go at this stage, with discussions about the development of the metre between 1792 and 1799. So in undertaking, let me go back to the map here, in undertaking revisions after 1744, Cassini de Thury extends his sightlines beyond France, into Holland and into the Low Countries, and after 1762, his sights, triangulation sights, are on Vienna. He wants, as he says, to unite trigonometrically the most beautiful towns in Europe, Paris, Vienna, and London. And so he extends his Enlightenment lines of earthly measurement towards Dover and Britain. As he does so, he recalculates London's latitude, observing that, in fact, British astronomical calculations were inaccurate. An inaccuracy and uncertainty of 15 seconds, he says. In other words, the Brits have got London in the wrong place. This, with his and others' work, had of course important implications for the British view as to where London was. So Cassini de Thury's paper of 1776 on these matters is brought to the attention of Neville Maskelyne in the Royal Society in London in April 1785, and it's brought to his attention by Sir Joseph Banks. 2 years later, in a paper read before the Royal Society in February 1787, Maskelyne responds, and I quote, "To the doubts entertained by the late Royal Astronomer of France concerning the latitude and longitude of this Royal Observatory." You're beginning to get, I think, some sense of the tension that now emerges in the course of the following 10 years or so. Now, the details of this paper, Maskelyne's 1787 paper, really, I don't think need concern us. He draws upon a whole series of different observers' reports and a whole series of calculations over the differences between the two meridians that are made in the period between 1773 and 1785. It's a 12-year observational period, and they use essentially different methods too. So we are told that the difference between Paris and Greenwich in March of 1776 was 10 minutes and 46 seconds, but we should be cautious, he says, because the air was hazy in Paris from the observatory that day. In August of 1783, the air was very clear in Greenwich, and the difference is 8 minutes and 54 seconds. Overall, these 12 years of calculations produce a mean difference between Paris and Greenwich of 9 minutes 31 seconds. Between 1775 and 1786, a further set of 40 calculations is undertaken between the meridians of the observatory at Greenwich and the Hôtel de Cluny in Paris, which is 2 seconds east of the observatory. Why it's taken in Cluny and not the observatory, I don't know, but it isn't. The assessment of their mean, that is, of the average overall, means that the difference of the two observatories was 9 minutes 20 seconds. That's the average that they come out with. A series of observations over this period. Maskelyne goes on to cite yet further evidence. He includes evidence from the French. It's not that he's doing a whole series of British work and not recognising the French work. He includes Pierre Méchain, who's editor of the Connaissance des Temps, and who later, in fact, is centrally involved with plans for the establishment of the metric system in revolutionary France. And Maskelyne goes on to propose a compromise of the differences expressed. For the present, I infer, at the end of Maskelyne's 1787 paper, we may take the difference of meridians 9 minutes 20 seconds as being within a very few seconds of the truth. Till some more occultations of fixed stars by the moon already observed, or hereafter to be observed, in favourable circumstances and carefully calculated, shall enable us to establish it with the last exactness. The degree of difference is not what's important here. What's important in this part of the story is the emphasis upon the idea of the last exactness being only ever a working figure, being within a few seconds of the truth, as Maskelyne puts it. And recall that Maskyline's solution is based upon mathematical computation. Until, he says, new work is done, let's rest at that. That'll have to do. His work is essentially, if you like, in Latourian terms, based on a centre of calculation in London. But the man who addresses the problem in the field is the Scottish military surveyor William Roy, who in 1787 is recognised by Maskelyne. Roy is by this time already undertaking work on what will become in Britain the Ordnance Survey, identifying a baseline for Britain's trigonometrical survey on Hounslow Heath, what is essentially now Heathrow Airport. And Maskelyne recognises that this trigonometrical baseline, if extended across the Channel, could be used, and I quote Maskelyne, to determine the difference of meridians of Greenwich and Paris to great exactness. And Roy produces a very lengthy account of his trigonometrical operations, of which this map is one that appears in the paper in the Philosophical Transactions of the Royal Society in 1790, to determine the difference between the prime meridians of Greenwich and of Paris. It's an absolute tour de force of late Enlightenment geodesy, quite in keeping with Cassini de Thury's Méridienne Vérifiée and Cassini IV's Description Géométrique de la France. It's a key work, in fact, also behind the establishment of Britain's Ordnance Survey. So, on the 23rd of September 1787, Cassini IV, Pierre Méchain, and Adrien Marie Legendre of the Académie des Sciences are standing on the cliffs of Dover, with meeting Roy and his fellow surveyors to begin a sequence of observations whereby the position of the two national observatories might be fixed by trigonometry and the two nations brought closer together, trigonometrically speaking. The British make use of a new theodolite designed by the instrument maker Jesse Ramsden, and they also have access to a John Harrison chronometer courtesy of the Board of Longitude. On the French, they have access to Lenoir and Borda's repeating circle. And so, with these instruments, a series of sight lines and triangles is drawn up along the south coast when the weather permits and extended into France. Gunpowder explosions are let off on the cliff tops to effect alignment by sight and by sound. Where possible, the angles and lines produced by this new triangulation are compared with both Cassini IV's Description Géométrique and with his father's 1744 Meridienne Vérifiée. They have the texts to hand in the field as corroborating devices. After 48 British and French triangles had been drawn up and compared, a reported difference of 15 inches was testimony, wrote Roy, and I quote, "To what a wonderful degree of accuracy operations of this sort may be brought when fine instruments are made use of and great care bestowed in the application of them." Oh dear, because Roy's confidence was greatly misplaced. The figure that they determined of the difference between the meridians of Paris and of Greenwich was 9 minutes 19 seconds, or it's actually 9 minutes 18.8 seconds. But these inquiries appear to suggest, assuming the British-based triangulation that Roy had done in getting as far as Dover was correct, that those farther east and west were not. In other words, that all the longitudes of the great map of France, the labour of more than half a century, will, to quote Roy, be considerably affected thereby in proportion of the distances of the places eastward or westward from the meridian of the Royal Observatory at Paris, respectively. Simply, what Roy is suggesting is that France is now the wrong shape. The search for precision had uneven national consequences. Much as had been the case, a century before, the very clear implication from Roy's commentary was that France in about 1789 was less certain in its shape and size nearer its coastal margins than it was down its prime meridian. For Roy, the solution lay in the conjunction of different methods: trigonometry, a timepiece, Harrison's chronometer, what he calls the next best mode to angular measurement. This is actually setting chronometers in relation to the repeated instantaneous explosion of light. In other words, he lets off explosions on the cliff tops and measures and computes in that way. Finally, he says, locating the two prime meridians lay in repeated astronomical observation. So by the 1780s, late 1780s, fixing the two prime meridians in space appeared to be only a matter of time. The solution would be arrived at via, in Roy's words, mathematics, instrumental accuracy, patience, and the regular use of gunpowder. Taking into account adjustments relating to the curvature of the Earth, the calculations of this joint Franco-British venture produced two results to provide the separation of the meridians of Greenwich and of Paris. And I am coming to a conclusion in just a moment. 9 minutes 20 seconds, 9 minutes 18 seconds. This latter was very close, of course, to Roy's figure of 9 minutes 18.8 seconds. This is even closer. The former figure, 9 minutes 20 seconds, is closer to that compromise figure derived from Maskelyne and Cassini 3 and others based upon the astronomical calculations between 1773 and 1786. In other words, we have different figures. We haven't resolved where Paris and Greenwich are. The exact position of the two prime meridians is uncertain, and for the French, Roy has just told them that in fact their nation east and west of their Parisian prime meridian is not accurately determined. The Franco-British triangulation project of 1787 to 1790, this is Roy's map of 1790, may not have agreed exactly where the respective prime meridians of Greenwich and of Paris lay, nor did it mark accurately the distance between them, the calculative difference between them. But what it did mark was a phase of genuine international collaboration. This stops, for a variety of obvious reasons, between 1790 and 1815. For the British in this period, they continue with the Ordnance Survey. For the French, between 1791 and effectively 1799, of course, Méchain and Jean-Baptiste Joseph Delambre are going off and calculating the meter and doing their meridian arc work from Dunkirk in the north to Barcelona in the south. But in 1817, the French resume planning to again map their nation, with Roy's words at the back of their mind. And in 1821, the British and the French again resume collaborative inquiries about the Greenwich-Paris measurements. And with these, I will close. Responsibility on the British side in 1821 for the resumption of operations for connecting the meridians of Paris and Greenwich rested with Captain Henry Cater and Captain Thomas Colby. Colby, later the director of the Ordnance Survey and a hugely important figure in the mapping of Ireland in the 1820s and 30s. Cater's capacity as metrologist and surveyor had been honed in India during his apprenticeship to William Lambton and the work on the Great Trigonometric Survey there, and by his work in Britain from 1814, because Cater is essentially the person who's responsible to the Royal Society and to the Parliament for the regulation of Britain's weights and measures, the threat that the French revolutionary meter is seen to pose to the establishment and the continuation of Britain's imperial units. Colby and François Arago several times then crossed the channel between Folkestone and Calais in the autumn of 1821. But one of the difficulties that they encountered was in relocating the exact spots in England that Roy had earlier employed. A mill that Roy had used earlier for his lines of sighting has been demolished. One of the guns marking the ends of his baseline at Hounslow Heath had been removed, stolen, melted down, lost. Geographical observation then and geometric calculation based on accurate and careful positioning was thought much more likely to produce accurate results than astronomical reckoning, but nobody could find Roy's base points against which Cater's work should be undertaken. Despite such claims, accuracy was compromised, as they recognised, in several ways, by the unsteadiness of the building at Hanger Hill Tower. They erect a viewing point at Hanger Hill Tower that wobbles in the wind. by the fact that the intervening smoke of London meant that only once was the signal erected upon that tower actually seen, and because by mid-November 1822 the men who were actually involved in establishing this theodolite in these several stations were suffering the effects of working the whole summer through, as one commentator put it, upon a wet and clay soil. But not the least of the difficulties, reported Cater, was the fact that William Roy, his map here of 1790, had used different linear measurements than those now in use by the British through Cater in his establishing the imperial units. By the comparison of various British standards of linear measure, it appears that the standard employed by General Roy for the measurement of the base upon Hounslow Heath differed from the imperial standard yard. And in consequence, it becomes necessary to there's a bit of detail here that in a sense kind of makes the story all, but you don't need to remember this bit of detail. In consequence, it becomes necessary to multiply General Roy's distance by 0.000691 to obtain 5.82. The correction, says Cater, that is to be added to such distance in order to convert the feet of his survey into imperial feet. So the British here are recalculating themselves because Roy has used an old form of imperial measurement. Thus, Cater says, the sides of the trigonometrical survey of Great Britain are, I believe, derived from bases measured by General Roy's standard, and they will therefore require the same correction as that employed above, should it be necessary to convert them into imperial feet. Let me conclude and make clear the point I'm making. In 1790, William Roy had cautioned the French that their measurements had miscalculated the extent of France, just as the French had recalculated France anew in the 1690s. But in the 1820s, Henry Cater counselled that William Roy's metrology, and indeed the whole mapping of Britain, similarly required adjustment to take account of different standards. He'd used an old form of imperial units. Now, if fixing the prime meridian depends vitally upon the use of a standard metrology, then the reverse is also true, that in order to represent terrestrial space in map form, the prime meridian or other baseline must be accurately known. Cater knew this. That's why he's so ticked off to find that Roy has used an old unit. The truth of the preceding work, he says, in 1828, wholly depends upon the degree of reliance that may be placed upon the base on Hounslow Heath, and as the accuracy of this is in some measure questionable, it is certainly desirable that a new base should be determined. And so, in 1825, they send out astronomer John Herschel, armed not this time with gunpowder, but with rockets. Rockets, this is the rocket in the American national anthem, Rocket's Red Glare. The series of rockets are fired from the observation points established by Colby on the English side and by François Argot on the French side. Triangulation and calculation follows. At each station, teams of observers working to coordinate things, eyes to the rocket's red glare, rocketry to chronometry, chronometry to trigonometry, all with a view to calculating longitude. In July 1825, Herschel, providing testament, he says, to the rigorous methods uniformly applied, gives the results. On the whole, then, 9 minutes 21 seconds may be assumed as a result not very likely to be altered a whole tenth of a second, very unlikely to be altered to twice that extent by future determinations. The importance then, and finally to wrap up, the importance of the Franco-British endeavours between the late 1780s and the later 1820s rests, I think, much less in the point of the results obtained for the relative position of the Paris and Greenwich prime meridians. What is of interest, or in part I think interest in the bigger picture of the prime meridians, is the picture that is disclosed of the methods and of the metrologies. The problem of determining accurately one nation from its prime meridian, or in fixing different prime meridians relative one to another, the problem lies in a combination of things. The metrology employed in the baselines used, as the French discuss of themselves, as Roy discusses of Cassini de Thury, as Cater discusses of Roy. The period of observation is also important. Of course, the number of measurements taken, the instruments employed, the calculations made, but it's actually crucially a story about the capacity for error and the trust in one's fellow operatives. What sustained the different personnel involved, men like Méchain, Roy, Cater, Arago, John Herschel and others, what sustained the different personnel in fixing the positions of the Paris and Greenwich meridians was the idea of accuracy in an absolute sense. But the accomplishment of accuracy was always a relative achievement, always something constrained and contingent upon very local circumstances. And it's actually, in this sense, a story about operators' tolerance of their results and of one another and of error. Thank you. Sorry, yes.